For decades, facility managers have treated biological contamination as a surface cleaning issue, but invisible threats move through commercial building systems long before they breach a wall or ceiling. Relying on visual inspections and subjective smell tests leaves commercial properties completely exposed. By the time contamination is visible, the building envelope has already failed. Modern environmental assessment requires a transition from estimation to absolute metrology. We now rely on standardized measurement, traceable to international scientific benchmarks, to quantify the exact conditions of an indoor environment. Achieving structural dryness is a strict engineering problem. It demands military-grade precision to verify that the physical boundaries of a space are entirely devoid of excess moisture. Diagnosing a building requires mapping two distinct datasets. First, we capture instantaneous spatial data to locate current saturation. Second, we record time series environmental data to uncover intermittent thermodynamic failures over time. Executing this requires a technological arsenal, from targeted moisture meters up to autonomous robotic reconnaissance units that map the infrastructure from the inside out. Without calibrated empirical data confirming these conditions, any remediation clearance is scientifically invalid and legally indefensible. Every fungal network in a built environment is catalyzed by a single variable, uncontrolled thermodynamic moisture. To locate that moisture, investigators use psychrometries. This is the scientific study of the physical and thermodynamic properties of gas-vapor mixtures, specifically the relationship between air temperature and the moisture content it can hold. This chart shows the interaction between relative humidity and temperature. Where they intersect, they establish the dew point. If warm, humid air contacts a surface below this dew point, vapor condenses into liquid water right on the material, providing the microclimate spores need to germinate. To map the extent of this liquid water, inspectors deploy professional moisture meters. These devices provide real-time, quantitative data on the precise moisture content trapped within specific building materials. Deep substrate analysis requires pin meters that penetrate the material to measure electrical resistance, while pinless meters use electromagnetic signals for rapid, non-destructive scanning across large surface areas. These instantaneous readings tell us exactly where the moisture is located right now, but they cannot reveal when the moisture arrived or why the failure occurred in the first place. Spot checks with handheld meters often miss the root cause of an infestation. Mold growth frequently results from intermittent environmental failures that only appear under specific conditions. Historically, tracking these changing conditions required large mechanical chart recorders that plotted temperature and humidity data onto rotating paper drums. Today, we deploy miniature digital data loggers. These discrete sensors are placed throughout a building for 2 to 4 weeks, continuously monitoring the environment without disrupting the occupants. A primary target for these loggers is identifying a thermal bridge. This is a specific structural defect where heat bypasses the building's insulation, creating a localized cold spot prone to chronic condensation. This chart shows time series data captured by the loggers. By recording parameters up to 50 times a second, we can see exactly when outdoor temperatures plummet and indoor relative humidity spikes into the danger zone above 60%. Correlating this indoor data with outdoor weather patterns isolates the exact mechanism of failure. We can determine definitively if the moisture is caused by a structural defect, like a roof leak, or by occupant behavior, like inadequate ventilation. Deploying long-term data logging replaces reactive emergency responses with proactive forensic building science. With the physical structure analyzed, the investigation shifts to indoor air quality and the concentration of airborne threats. The optical particle counter provides instantaneous counts across multiple size channels. The 0.3 micron channel indicates hidden active mold colonies. Conversely, high concentrations in the 10 micron range point to a mechanical failure, suggesting HVAC filters are improperly installed or completely compromised. Because this data is instantaneous, teams can screen rooms for contamination and verify the integrity of negative pressure containment barriers on the spot, rather than waiting days for laboratory analysis. While particle counters successfully pinpoint the exact location of a biological hotspot, they are strictly non-viable sensors. They count the particles but cannot identify the biological species, demanding an escalated testing protocol. To profile the specific biological threat, we deploy viable air sampling. We use spore trap cassettes attached to calibrated pumps, pulling exactly 15 liters of air per minute to capture actual biological material for microscopic lab analysis. A common misconception is that hitting a flat threshold of 1,000 spores per cubic meter automatically constitutes a failed clearance. Absolute numbers are meaningless without environmental context. The true metric for relative moldiness is the indoor to outdoor ratio. We must compare the indoor spore concentration against a simultaneous outdoor baseline to understand what is actually anomalous. This chart compares an outdoor baseline to indoor contamination. When the indoor to outdoor ratio exceeds a 2-to-1 margin, or if the species distribution completely shifts, we have definitive proof that mold is actively amplifying inside the building envelope. Evaluating indoor air without that comparative outdoor baseline strips the data of its context, rendering the assessment scientifically invalid and highly vulnerable in a legal dispute. Even with advanced instruments, human inspectors face severe physical limitations when assessing multi-story facades, structurally compromised crawlspaces, and internal ductwork. To overcome this, we deploy unmanned spatial diagnostics. Drone-based infrared thermography allows for rapid, comprehensive scanning of massive commercial building envelopes. These thermal imaging cameras map surface temperatures to identify hidden moisture patterns. Because wet materials evaporate water, they appear as stark cold spots on the thermal display, allowing us to locate leaks without destructive testing. For ground-based hazards, heavy-duty four-wheel drive robotic crawlers navigate mud, debris, and tight clearance crawl spaces, transmitting high-definition visual data from environments too toxic for human entry. Inside the building's respiratory system, HVAC-specific robotics execute targeted missions. These tethered units travel deep into the ductwork, targeting primary distribution pathways of biological threats. Beyond inspection, these units utilize pneumatic whips to clean surfaces and airless sprayers to seal ductwork with antimicrobial encapsulants, neutralizing future HVAC failures. Unmanned robotic systems systematically eliminate the diagnostic blind spots that traditionally allow biological threats to survive and recur. Deploying isolated gadgets and conducting piecemeal testing is insufficient to resolve systemic commercial building failures. This diagram illustrates the necessary convergence of data. Instant moisture readings, continuous psychrometric logs, particle counts, and robotic visual feeds must synthesize into a single, cohesive digital dashboard. This centralized intelligence integrates directly into the facility's building management system, automatically triggering targeted remediation work orders based on empirical data. The integrity of this entire command structure relies on rigorous instrument calibration. Sensors must maintain metrological traceability to national standards to ensure completely objective data. This framework replaces the subjective guesswork of legacy visual inspections with a strictly objective, data-driven methodology. Implementing this system generates highly accurate, legally defensible compliance records. It provides an unbroken chain of custody for environmental data, protecting occupants from exposure and owners from liability. The facility transforms from a state of vulnerable uncertainty to being comprehensively mapped, secure, and under tight environmental control. By enforcing tactical discipline and utilizing advanced metrology, facility managers eliminate the variables of guesswork and restore absolute operational readiness to the building.